Well, good morning, everybody. It's good to see a crowd in here, even though it's fairly early in the morning. And I know some of you had one or two great beers last night, and maybe more. This morning, Russell is going to tell you if Groovy is as fast as Java, and please go ahead.
Thanks, Aaron. Hopefully this is not going to get too loud as I jump up and leap about and stuff. If it does, we'll turn it down. Of course, you all remember that tomorrow is Towel Day, so I hope that you will all be wearing the lilac. Good. One or two people actually know what I'm talking about. If you don't, go and learn about Hitchhiker's Guide to the Galaxy. If you don't already know about it, you should. Anyway, is Groovy as fast as Java? We've got 50 minutes. Okay, we're finished. You'll notice clever use of fonts here. So when you see a change of font, think of change of voice. This font are the Scala people. And they were going to say, oh, I should also apologise that you're not going to be able to read the slides because it's cut off over here. It's not cut off here, and it's not cut off over there, but it is cut off up there. And Søren is annoyed, and I told him with 5 minutes to go before the start, forget it, we'll deal with it. So I will in fact read these slides occasionally, just to make up for that. And in this particular case it says, obviously so, Java is a statically typed compiled language, and Groovy is merely a dynamic scripting language. Ergo, no way is Groovy ever going to be as fast as Java. Let me introduce you to the tortoise and the hare. I think most people have probably come across this tale. The tortoise and the hare have a race, and of course the tortoise is never going to win on the grounds that it goes a few steps a minute, and the hare sort of bounded off into the distance. Have people actually heard the story and know what the resolution is? Yeah, okay, so stack that one. Or actually, I suppose we're all Git users, so stash it, and we'll use that one later. Having made the statement that Groovy is clearly not going to be as fast as Java, we ought to get rid of the prejudice side of things. So we're actually going to need some proof that the statement that we're trying to make is true. So proof, I'm thinking, the first thing I think of when anyone talks about proof is proof spirit, on the grounds that the whiskey is very good. No, that joke's not gone down too well. Perhaps you guys had too much beer last night and are thinking the whiskey wouldn't go on top of it. Let's forget that joke. So what we're going to do then is evidence the truth of a proposition. Well, that sounds like heavy stuff for a Friday morning at 8:30. So, you know, you're thinking that, and I'm thinking that as well. So we do have a bit of a problem. So I thought, proof. We need to cut down the problem. And we're talking about things like speed of programming languages. And so therefore I thought, how can we cut down the problem? Well, let's deal only with compute-bound things, and let's ignore the entire I/O problem. So all you people who are only interested in web interfaces, you're quite welcome to leave now, because I'm not going to talk anything about the performance of anything to do with the web. This is hardcore stuff. So we're going to have a compute problem, and given my history in this community and most other communities, you know exactly what the problem is going to be, and it's going to involve pi. We didn't have any of that last night, it was all sausages, but we're still going to deal with pi this morning. I'm going to ask you the question, what is the value of pi? Anyone actually know what the value of pi is? Eh? We know exactly the value of pi. It's pi. Yeah. Sadly, anyone recognise? Oh, yeah, one person will recognise this. Okay, so the adverts haven't got to the continent yet, so that doesn't make any jokes. So we better talk about these guys. Meerkats, they know about pi. Look at the way they're standing. They know exactly about pi. Oh, what's he doing here? Oh, that's right, doesn't want pi at all, wants nuts and seeds. Okay, so approximating pi. We need to have the computers understand the notion of pi, and you see down there at the bottom an integral equation. And this integral equation is something we could solve because we're clever, and computers can't because they're dumb. No, that one didn't go down too well either. But we're going to need some form of approximation so that the computers can actually deal with it, and so you come up with these sort of sums. Actually, computers are quite good at sums, unlike humans. So here we're now in computer territory. And the problem we're solving is quadrature. So we're putting rectangles under curves, trying to find the area under the curve. So conic sections invariably involve some form of circles and areas under curves and radiuses and stuff like that. And so we put these rectangles in because height times width, easy to do. Lots of them. I've shown a picture with 3 there. That's not a big problem, but the big problem is when you give it 10 to the 7 or 10 to the 9 little rectangles. And then we're going to iterate over 10 to the 7 or 10 to the 9 rectangles, summing up the area of them to gain an approximation to this value of pi. We clearly have a pending issue. Fast battery change. Right, so it's... it really doesn't want you to get in there, does it? Hello? Yeah, well, whatever the Danish equivalent of voila is.
We use voila.
Voila will do then. My pronunciation is probably appalling, but Cedric will correct me later. Surprisingly, you might say, there's going to be no mention of parallelism in this talk. Because parallelism destroys the ability to predict anything about what's going on. So we want pure sequential, single core, which is pretty useful because multi-core timings can be really problematic because you get threads moving around between cores. So let's just dispense with all that, dispense with parallelism. So we're talking about single-threaded performance. So I'm not even going to mention GPARS. No, I'm not going to mention GPARS. So what's the test rig? If we're going to take numbers, we need to write down what the test rig is, because just saying that program A runs faster than program B is an abstract concept, completely useless way of doing things, because you need the context. Reproducibility of the results is a crucial factor. So here's the test rig, Lenovo X201. i7, you think immediately quad core. Would you think quad core if I told you it was an i7? Sad. Yeah. Most people think i7 equals quad core. I used to. And then I discovered that when you have an M in the number, it means that they're lying. And it's actually only a dual core. And then they make the claim that it's an M for mobile, and therefore it uses less power, and therefore you're not allowed to have 4 cores. I do wish they'd understand that iPhones already have 4 cores in them, and this is supposed to be a laptop. But there we go. I'm also going to switch off all hyperthreads, because hyperthreads are a disaster area when it comes to any form of performance monitoring. So single-threaded, no hyperthreads. The operating system we're using, as you know, I refuse to use Windows on the grounds that it costs money, and it doesn't work. Though, to be fair, the latest releases of Windows at least have a scheduler that does approximately work, unlike anything from XP and earlier. But I'm sort of a fairly unstable kind of guy, so Debian Unstable suits me. And as you can tell, Java 7 is just ancient history, as far as I'm concerned. Okay, so it's on here because Debian insists on having Java 7 on there. Actually, they insist on having Java 6 on there. But we just ignore those. We want proper Java. And so, therefore, Java 8, Lambda B88, and clearly these results are old hat and need to be redone, because B89 is now the one and only form of Java that we've got. And you'll notice that I'm using the Lambda version on the grounds that I like lambdas, and any form of Java that doesn't have lambdas in it is ancient history and should be abandoned. That's good. I'm liking the fact that some people are laughing at the humour. Sadly, though, not all systems, for example, IntelliJ IDEA, like the fact that OpenJDK exists and will only run on an Oracle system with hotspot. So sadly, the B88 of Oracle's Java 8 will probably make an appearance. We must expose the experimental method so that you can go out and reproduce the results. This is an important aspect of the scientific method, is that I've got an experimental result, I allow you to go and make the tests for yourself. That's an important thing. So here was the process that I went through. I made sure that the implementation of each of the algorithms was a function method of some sort, so that it gave the JIT the best possible access to this thing. So we're getting away from scripts in Groovy and all that sort of stuff. Be very, very definite about functions, so that we've got a particular code unit that we're making use of. When you're doing these sort of benchmarks, you don't do one run. You actually want to do a lot of runs. So although these things are working at microsecond iteration times, you want 1 to 10 seconds-ish of performance between the timing points. It reduces the amount of error that's going to be available in the experiment. I'm then going to call the function for 3 times, just to get the JIT warmed up, if it needs it. As an aside, I'm finding that Scala, Groovy and Java these days don't actually need warm-up time. It looks as though the JIT has gained precedence. It's actually predicting beforehand what you're going to run and getting the JIT warmed up for you, which is kind of weird. But what I'm finding is that those first 3 runs take the same time as the rest of them. So this appears, and this is just a hypothesis that would need testing, there appears to be very little in the way of JIT influence in these results. We then ran each of the functions 20 times to gather 20 data points. Statistically, you would be much, much better off if you had 60 or more. You can go into the theory of the statistics, and basically you need 60 or more data points in each of your data sets. But given that I have to actually do occasionally bits of work for money, which means I can't do this sort of stuff all the time, every day. I only had time to do 20 runs for each of the experimental points. From those 20, you create means, modes, standard deviations, and so on, so you can then do the statistical analysis. And of course, at that point, statistical analysis, you immediately think of R as the one and only programming language that will do statistical analysis. Would you guys think of using R for statistical analysis? 1 or 2 people are smiling, saying, yeah, they know about R and they know about statistics. And of course, R is now on its last legs, because Julia, the programming language, will take over from it, hook, line and sinker. Unless, of course, people discover Python and discover NumPy and SciPy and all the wonders of that. And of course in the Groovy community we have SFA to deal with statistical analysis. And I was beginning to think, how do I write a statistical analysis framework to analyse all this stuff? And I thought, no, I won't. I'll just do it by hand for the moment and worry about it later. So there's a call out now, if anybody's interested in doing statistical analysis packages for Java and Groovy, sign up, we'll go start a project and get something moving. What's the metric I'm actually working with? It's seconds per 10 to the 6 iterations. Notice on the previous slide I said I was going to make things run for 1 to 10 seconds. So that means each of these functions is going to be run a different number of times. And so we need to standardise on a metric that's going to be the same across the board. And so various divisions will be made to ensure that each of the experiments is giving us seconds per 10 to the 6 iterations. Now the values that you may or may not be able to see on the side of the slides here are going to be rounded for the purpose of display to 4 significant digits. Actually, I've been using doubles, so you can more or less guarantee 16 significant digits of floating point accuracy. If you're not aware of all the problems associated with floating point numbers, there are 3-year numerical analysis programs you can go on to teach you all about it. Anybody who thinks one floating point number can ever be tested for equality with another floating point number, please start again. Go to Go, do collect £200 and come back later. Okay, 1 or 2 people are humorous. It's very early. I realise we haven't yet got to 9 o'clock, which is the waking up time for people at conferences. So how are we going to do the analysis? Yes, it was a few hacked together Groovy scripts to do all this. But if you do this properly, you're wanting to worry about t-tests for comparing one mean with another mean, involving issues of standard deviations. You have to decide whether you're going to use one-tailed or two-tailed tests and stuff like that. And as you'll notice, I've actually been making use of Welch's variant of t-tests because we can't guarantee that the variance of the samples that we're taking is actually the same. And you then have to go away and do a 4-year statistics course to understand all that stuff. We don't care. We use the results. There are tables for all this sort of stuff. It's data lookup as far as we are concerned. If we want to do multi-mean analysis, you have to go into this wonderful field called ANOVA, analysis of variance, and it enables you to do 3, 4, 5-way mean testing. And I have to admit, this was another point at which paid work had to come first, and so I'm going to declare this a work in progress, and so there's more to be done after the conference before we can get some final results. It's also micro-benchmarking. I'm sure Jochen will laugh at this particular point in time, because it's a hard thing to do. And you look it up on the Google, and it tells you, ooh, Google Caliper is a useful tool for this sort of micro-benchmarking. Sorry, no it's not. Because Caliper insists on publishing any and all results publicly on Google. And I have no intention of doing that simply to get decent analysis. Lovely framework, useless mechanism it's embedded in. So again, we're going to have to do lots of handy waving at this particular stage. So, let's get into some codes. This is going to be interesting to see whether this works. So if I click on there, aha, excellent. Is that code viewable from the back there? Cool, thank you. I will have to change glasses on the grounds that this code is not viewable from here, even though that code is viewable from up there. I mean, if you're worrying about the rose-coloured glasses, it's to try and avoid migraines due to the 50 Hz in here. Go and study critical flicker frequency and stuff like that. So here we have pi sequential loop, a wonderful piece of Java programming. Is it not? Yes. The answer was yes. So is that the sort of program you would have thought of? I think yes, so here's the number of iterations, so it's 10 to the 9, various things. Here's the start time point. Let's assume that Java gets it right. The chances of it delivering nanoseconds accuracy is 0. It does, in fact, it's sort of hecto-nanoseconds, I think it's accurate to. And here's the actual loop. So we're going around the loop, summing stuff up. Horrible, hate these sorts of loops, but you have to do them. And we do the calculation, grab the time, and so on and so forth. So that's the basic Java unit. And you're thinking, horrible beastie, have we got something better? Of course we have. We could do it like this. Following all the things that Venkat told us to do yesterday, but in Java. Make it declarative. Get rid of all forms of update to your variables. Have you noticed the word final there? How many people use final in their code? Okay, so that about was a third. That means 2/3 of you are doing it wrong. Single assignment is a good thing for all the reasons that people have been talking about, immutability and the declarative approach to it. Single assignment. Variables, yes, but treat them as bound values that you can't rebind. And then you get much... Your code is requiring an awful lot less debugging, basically. So anyway, this is the Java 8. This is the reason for the Lambda version of Java being used. Same bit here, but now we're creating an in-stream range. So this thing lazily creates all the numbers from 0 to 10 to the 9. We then pass it through to map double, so it's going to apply this lambda expression to each of the values in turn, lazily, and then we ask for it to sum. And it's at that point that the take happens and the stream of values gets passed through. So this is the sort of Java that you will be writing from April 2014 onwards. It was supposed to be November 2013, yes, I know. But the Lambda folks were behind the... they got behind, shall we say. And I think Reinhold took the correct decision. It's egg on his face, because he said we must never slip a release. But I think Reinhold took the right decision. And yes, the London Java community was involved in making that decision. So it's also my fault that it got slipped in that sense, because I'm a member of the London Java community. This, though, from April, which should be the release of Java 8, will be the sort of code you will write. Notice the you will. Not you may, or you can, or you might think about, but you will. And if you're in organisations that don't like upgrading your Java, move to somewhere that does. Because I think we should abandon all organisations that are still on Java 5 and 6 tomorrow, and we should abandon all organisations that are on Java 7 from April the 1st, 2014. So we've had time to have a look through the code. It's fairly straightforward in that sense. So what about results? We need some results here. So we've got some results. So the Java simple loop, we've got a mean of 0.08, we've got a standard deviation. You look at the Java 8 version, you get 0.08 standard deviation. And what you're asking is, are these two values the same? So we make a hypothesis, we test it with the t value, so there's a big formula in which you chuck these two numbers, and out of it you get some number. The actual number is irrelevant. You go to a lookup table, but these two numbers here, you look them up in the lookup table and they will give you a value. And this value is a percentage chance that your hypothesis is right or wrong. So by saying these two numbers are the same, using the mean and standard deviation here, putting it through the formula, we get these numbers, and we get out 0.2 from the lookup table, which says there's a 20% chance that our hypothesis is wrong. So there's an 80% chance that these two numbers are the same. So that's the sort of thing we're looking at with these statistical analyses. We've got a couple of means, and you look at them and you think 0.08358, 0.08366, yeah, they're roughly the same. But we need to go one step further. We need proof rather than belief. And that's what this sort of analysis is for. But there is a little bit of uncertainty. It all goes with this, I didn't quite have enough time not working for money to actually get this fully done. So, idiomatic groovy. Let's have a look at some idiomatic groovy. Now, does this look like idiomatic groovy to you guys? I'll give you a minute and a half to have a look at the code, and then we'll look at an answer. Does that strike people as idiomatic groovy? Who would like to vote yes? Who would like to vote no? Okay, why? I like that one, especially after yesterday with Venkat hurling abuse at anybody who used a for loop. Quite well. I overstate the case there, clearly. I better say that because I'm being recorded. So this is going for posterity. So sorry, Venkat. Yeah, we've got a for loop. We shouldn't be going there if at all possible. But I did. We'll cover how to do it properly in a moment. But let me say, well, what's your expectation? Whenever you run these sort of experiments, get your expectation in your head first before you run the numbers. So what's people's expectation of the performance of that piece of Groovy? Okay, the slow. Very slow. Extraordinarily slow. Okay, so 109.3. Compare that with 0.08. So even with the standard deviation there is consistency on the standard deviations here. So we can be fairly confident. No, we can't prove it, but we can be fairly confident that the machine is randomly distributed. And of course, what we're now going to do is have a look at functional Groovy, exactly for the point that was made here. That's the sort of thing that I think these days we probably should be writing using the sum method with the closure here, providing the numbers. It's exactly the same pattern that we saw with Java. For loops transformed into integer streams. In Groovy, for loops transformed into higher order functions. Using the Java message, it's going from external iteration to internal iteration. So this is the influence of functional programming. It's not that we're doing functional programming, it's that we're hiding the loops in the library methods that we're calling. So the iteration is still there, but it's hidden in the method sum. Okay, I didn't time that one, as is noted here, mostly because I put it in the slides last evening. That's why I went after having only one beer. Well, actually I had two, and then a small amount of vodka, but there we go. Is Groovy as fast as Java? Well, I think it's obviously rolling on the floor, it's obviously laughing, and I'll leave it to you what the A and O mean. No way, no way. But why? Why is Groovy so extraordinarily slow? Well, it's the deaths. If you abdicate responsibility for your types, which is after all what dynamic programming is about, then you're in the lap of whatever Jochen wants to choose as a representation, or Cedric. And they want to choose big decimal because they like infinite precision floating point numbers, which clearly are extraordinarily slow. So, we're comparing apples with oranges. That's the phrase in the English. I don't know what the equivalent Danish might be, but completely different genus of fruit is what we're comparing. The Java, strongly typed, primitive types, the Groovy, big decimal and big integer. And at this point, of course, we're comparing apples with oranges, and she doesn't give a damn. She wants seeds and nuts and stuff like that. Apples and oranges just do not cut it. So what about an annotated idiomatic Groovy? And so here we're getting into, no, we are not going to allow the default types. We're going to get involved with formal specification of the types of these things, and I'm not worrying about anything with a capital letter. If it's got a capital letter, I don't want it. Not as a type, because I want to be down there in the guts of the JVM. This is going to be a bit weird come Java 10 when we get rid of all primitive types, but that's going to be fun. So that's the full code. Okay, yeah, we'll get rid of that and use sum in reality, but what's the performance of this particular code? Because this is what I've actually run. And the answer is 2.7. So by simply annotating the code with the primitive types, we've moved from 109 to 2. So that's like a 50-fold increase in performance. And if you were to do the t-test between those two numbers, given the standard deviations, you would find something of the order of 99.9% yes, that they are different. So those are just not the same number. You could then hypothesize that it was a 50-fold increase, use a t-test to test that, and you would come up with about 95% confidence that it is 50 times faster. That's cool, 50 times faster. But it ain't good. You know, Java was 0.08. So, well, okay, I got these in the wrong order, but then I'd already had the vodka by then. So this is just the proper Groovy, and I shall go away next week, week after, and run the numbers on these and get them up on the website, on my website, in a small blog, just to put this stuff on record so that Google indexes it and there won't be any lies spread. Okay, no numbers for that one, so no point in carrying on with that one. So statically compiled languages are clearly faster than dynamic languages, so let's use Groovy's capabilities. This is where Cedric starts cheering. So what about statically compiled Groovy? So we're going to do something of this sort. As I said, we must ensure that we've got a function. And so there we have a compile static execute function. It's exactly the same code as previously tested. So that for loop is still there for consistency. Again, you need to test the same code against each other. So what's the result of running that one? Ooh, 0.9. Standard deviation is quite small. So the sample's a thin normal distribution. And again, if you do the t-tests, you get about 90% confidence that this is, 98% confidence that this is different from the previous number. So statically compiled beats dynamic. You may cheer. Because I'm sure Cedric will be happy that we have a statistically significant result that says statically compiled is actually worth it in the performance stakes, which is great. But it isn't good enough. 0.9 is nowhere near 0.08. So you think, you're all using Groovy straight out of the can, and some of us compile it every morning. How many of us compile it every morning? Oh dear, I feel all alone. Ah, Jochen, you compile it 3 or 4 times a day. That's what it is. Right, excellent. But you're probably not using the indie artifacts. Is anyone actually using the indie artifacts apart from me? 1 or 2 people at the back. Excellent. So indie is supposed to be using the INDY. I knew I was going to forget this. Invoke dynamic. Thank you. Yep. As a footnote, remember that invoke dynamic is way more important than dynamic languages. Invoke dynamic and method handles is exactly what Java 8 is based on. So invoke dynamic is more important than JRuby, Groovy, Jython, and so on and so forth. It's core to the way in which Java runs as of April the 1st or whenever, 2014. So you will like invoke dynamic. So what I do is I replace the non-indie jars with the indie jars. Now if you don't then invoke them with the indie option, you just get the same behavior. Well, actually you don't, but we're going to have to talk about that after this session. So I ran all of those same codes, exactly the same codes, but using the indie switch. I'd already been using the indie artifacts on the previous numbers. So that's not a factor in this. I'm not comparing apples and oranges again, because my setup always was a Groovy using the indie artifacts. So this was just switching on the indie option to the compilation and then running. And the numbers are roughly the same, you think. So you make a hypothesis, you run a t-test, and basically this is going to be a bit different. It's not quite as good, but I want to go to those 60 sample before I start making definitive statements. With only a 20 sample, you haven't got enough degrees of freedom to start making definitive statements about the difference between 109 and 111. So what I'm indicating here is the sort of scientific method we've got to go about when we're making these sort of claims of, is Groovy going to be able to beat Java? Well, clearly in this case, we're not. Indie has done very little for us at this stage. 111, 109 is the same, 1.2, or it was 1.3, 0.9 something, 0.9 something. Those numbers are roughly the same. The indie has not changed it. So is Groovy as fast as Java? Well, sadly it seems not. 0.9 is like roughly 10 times slower than the Java code. So we're going to cry because we want to use Groovy for serious heavyweight computation, compute-bound problems. There's always a but in these statements. So let's have a look at getting really dirty. There were not enough people in Venkat's talk yesterday, clearly. This is now getting really down and dirty, yeah? I feel unclean. That's possibly because I didn't have a shower this morning, but that's mostly because I had to be here at 8:30. Okay, so people have had a chance to look at it. The only real difference is the for loop, to be honest. We've changed the for loop. If you go and do a side-by-side comparison between this code and the quasi-reasonable code where we use the for I in range, you'll notice the only difference is that for loop. I'm showing up the wrong one. I don't know. Where's the power? Okay, so there's been some fault in which ones I've linked to, because I've always used the multiplier. I didn't actually use power at all, because using power is a bit slower. So I've been using the hardware multiplier for all the numbers. So if, I should be looking at these rather than looking at you. But one of the speakers is supposed to interact with the audience, and associate with the audience rather than look down here and to do this sort of thing. So I wasn't reading my slides properly. If there was any power functions in there, those were not the ones actually tested, because I thought power, I took an assumption that power is going to be slower than explicit multiplication. Okay, it was a leap of faith, and here in a talk on using statistics and actual numbers, having leaps of faith does seem like a bit of an irony, but there we go. So apologies for that. No, all of the numbers were done using the multiply version. Well, it shows somebody read the slides. Excellent. So are you ready? What's your expectation? Oh, someone made a comment there, holy crap. This is repeatable. I'll go back a slide. I didn't believe it. I just kept going on and on running this damn thing. I ran it in Starbucks, I ran it in Brew, I went almost everywhere and kept on running it. And it's reproducible. Now, there are so many variables here, of course, that it's reproducible on this machine with that code, time after time. I'll give the machine to someone, they can run it. It's repeatable time after time after time. The question is that repeatable on your kit? So again, Cedric, Guillaume, and Jochen have often talked about the numbers, where they have that 4 tables, and one of them is actually a version of this code. We do need to do some more statistical analysis. Getting numbers like this is such a shock that we have to do some really deep statistical analysis. But I'm still here. I'm sorry, I'm still here. But you have to dive into the mud to get there. But anybody who's involved in this optimizing of compute-intensive code realizes that beautiful code sucks most of the time. It's okay for web application developers and stuff like that. But when you're doing serious computing, you know, Fortran in 2013, for example, your code generally looks horrible. But it's the tight loop that looks horrible. Everything else can be beautiful. But you have to look for the tight loop, the for loop in this particular example. That's where you have to lose the beauty in favor of really optimizing everything to the maximum. This sort of statistical analysis, as another footnote, any people heard of LMAX? A company called LMAX? 1 or 2 people here. They did some very, very deep analysis of the use of Java in event frameworks in order to create a lock-free ring buffer. And they actually analysed Java code running on a JVM, running on Intel kit. And what they were measuring was the cache line. So your measurements are at the hardware level for Java running through all this. And because of that, and that sort of statistical analysis, they've come up with a lock-free data structure, ring buffer, which is at the heart of a thing called the disruptor, which is a beautiful piece of event processing. So if any of you are interested in this sort of performance stuff for things like financial transactions and stuff, go and have a look at the disruptor. It's well worth it. Okay, back to our glee that we've slaughtered Java in terms of performance. I thought, you know, the original tortoise and the hare, the tortoise won because the hare got complacent. Remember Venkat talking about complacency kills. That's at the core of why the tortoise won in the tortoise and the hare. We've taken a different approach. We've just got Jochen to put the rocket fuel into Groovy by highly optimizing that one particular for loop. So is Groovy as fast as Java? Well, the moral of the story is really making claims of this sort requires statistical backup. Any other way of making these claims is fatuous. So if we're going to start talking of this sort of stuff, we're going to have to do micro-benchmarking, we're going to have to get involved in statistical analysis, creating these sort of experiments. And I've given an indicator here of the sort of thing I'm going to be doing going forward. This is a work in progress, very much. I had hoped to have a little bit more on this, more proof and more t-values and the actual AVA, but I will be continuing doing this, as I say, put it up through blogs and so on and so forth. But at this stage, the real answer still has to be no, in reality. And so we're back with the sort of Scala Java folks who wouldn't have believed that number. They definitely will not believe that number. You can guarantee it. They will be hunting for what's wrong. I'm confident the number will stand up, but I've got no proof of that because I've been the only person doing this. And it needs others to join in this sort of work to make these sorts of proofs. The statistics in this case are a bit in need of more work. There is no doubt about that. But they are indicators. They give me confidence that this stuff is worth doing. It's worth persevering with. And so I shall be certainly doing more work along these lines, and it would be great if other people would get involved. And so that's really the message. It's rounding out. Groovy isn't as fast as Java, and actually in most cases it's unlikely to be, exactly because we are going to write beautiful code. Most of our code should be beautiful. We shouldn't care about performance, because probably 99.9% of code is not performance critical. It's that 0.1% that is critical, and that's where we go and focus. You've got to do the statistics to find out where those points are. And so with that, I'm going to run over by 2 minutes. I had intended to leave 5 minutes for questions, but we've only got like 3. So are there any questions that people have got on this? You've been quite quiet. And yeah, I stopped doing jokes for a while, so because it got a bit serious. I didn't want to mix the humour with the actual really serious message, which may or may not have been a good thing at this hour in the morning, but there we go. Are there any questions that people have? Or you just sort of want to go back to this slide and just say, that'll do me fine? No, in which case, thank you very much for coming and being a great audience. And if you've got any questions, we can do it after the next session. Thank you very much.
Yes, and I also want to thank you for coming, doing this presentation. Next up in this auditorium is a Griffin update with Andrews Allery, and if you rather want to go see good forums with Peter McNeil, you should head over to Auditorium 1. We will start again at 9:30.